Welcome to Sleepy Earth Channel. Tonight, we're diving into a lost world hidden beneath ancient oceans, a time when giant sea monsters, larger than buildings, ruled the waters long before humans ever existed. Together, we'll explore the terrifying rise of massive marine reptiles, prehistoric sharks, and the mysterious oceans that once covered Earth. Before we begin, leave a comment telling me what city you're watching from tonight. And let's slowly drift back into the ancient seas of prehistoric Earth. More than 200 million years ago, long before human beings ever looked across an ocean and imagined it peaceful, the seas of Earth belonged to something else entirely. Not whales, not sharks as we know them today, and certainly not anything a modern person would recognize as familiar. The oceans of the ancient world were larger, warmer, and in many places far stranger than the water covering our planet now. Entire coastlines existed where no land remains today. Shallow inland seas cut through continents that no longer exist in the same shape. Storm systems moved across a greenhouse Earth with almost no polar ice, and beneath those dark prehistoric waters lived predators so enormous that even modern marine biology struggles to fully compare them to anything alive today. It is easy to imagine ancient Earth as a world ruled only by dinosaurs, because their skeletons dominate museums and movies. But for much of prehistoric history, some of the most terrifying animals on the planet were hidden below the surface of the sea, far away from sunlight, where the rules of survival became colder, quieter, and infinitely more brutal. One of the strangest things about those ancient oceans is that they did not simply produce larger versions of modern animals. They produced entire body plans and ecosystems that feel almost alien now. Some reptiles evolved into shapes that resembled dolphins millions of years before dolphins existed. Others developed jaws large enough to seize prey nearly the size of themselves. There were armored fish that looked like moving tanks, squid-like creatures with hooks lining their limbs, and giant marine hunters capable of crossing enormous distances through open water long before humans ever built ships. And unlike the modern ocean, where large predators are relatively rare and spread thin across vast habitats, certain prehistoric seas may have supported dense layers of competing giants living side by side. In some regions, almost everything large enough to notice was also large enough to kill you. The deeper scientists study these ancient ecosystems, the more unsettling they begin to appear. Modern oceans already feel mysterious to most people. We still know surprisingly little about the deepest parts of Earth's seas. But prehistoric oceans add another layer of uncertainty because much of that world has vanished almost completely. Ocean floors are constantly destroyed and recycled by plate tectonics over millions of years. Unlike forests or deserts, ancient seabeds rarely survive intact for scientists to study. Much of what we know comes from fragments buried in cliffs, dry valleys, or mountains that were once underwater. A single fossilized vertebra found in a desert can reveal that an entire sea once existed there. Sometimes, a massive tooth or skull fragment suggests an animal of impossible size. Yet, the rest of the creature is gone forever. In a way, the prehistoric ocean is reconstructed almost like a crime scene, with most of the evidence missing. And that uncertainty creates a strange tension in paleontology. Some ancient marine animals may have been even larger or more bizarre than current evidence suggests, while others may have been exaggerated by incomplete fossils and public imagination. There are moments where science becomes cautious, because the deeper into prehistory we go, the harder certainty becomes. Yet, even the conservative estimates are extraordinary. Some marine reptiles grew longer than school buses. Some fish possessed bite forces capable of crushing armor and bone. Certain ancient sharks likely occupied ecological roles so dominant that entire migration patterns of prey animals may have revolved around avoiding them. And perhaps most disturbing of all, these giant predators were not isolated monsters. They were products of stable ecosystems that lasted millions of years. Earth was not briefly experimenting with gigantism. In many eras, gigantism was normal. One reason ancient oceans could sustain such enormous life may have been their structure. During several prehistoric periods, sea levels were dramatically higher than today. Vast, shallow seas spread across continents, flooded coastal plains, and created warm, nutrient-rich habitats filled with fish, ammonites, and primitive marine reptiles. These shallow environments became biological engines constantly producing food. Combined with warmer global temperatures, certain regions may have supported incredibly dense food chains. The ocean was not empty blue water in the way humans often imagine it now. In many places, it may have resembled an endless battlefield hidden beneath the surface, where predators hunted continuously through forests of marine life stretching for hundreds of miles. Oxygen levels may also have played an important role during parts of Earth's history. Although the exact relationship between atmospheric oxygen and body size remains debated depending on the species and time period involved, some prehistoric intervals likely allowed larger body structures to function more efficiently than they would under different environmental conditions. But oxygen alone does not explain these creatures. Evolution itself tends to escalate competition when ecosystems remain stable long enough. If prey animals grow larger or faster, predators adapt alongside them. If one hunter becomes more efficient, others must compete or disappear. Over millions of years, this evolutionary arms race can create animals so specialized and powerful that they seem almost exaggerated. The ocean amplified that process because water supports weight more effectively than land. On land, gravity limits size. In the sea, those limits loosen. A creature weighing dozens of tons can move with surprising grace underwater. That single difference changed the history of life on Earth. It allowed the oceans to become the birthplace of some of the largest predators the planet has ever seen. And yet, there is another possibility that makes the ancient seas even more unsettling. Some scientists suspect that the fossil record dramatically underestimates the true scale of prehistoric marine ecosystems. Large ocean predators die in open water, far from conditions ideal for fossilization. Bodies decay, sink into deep sediment, or are scavenged before preservation can occur. Entire species may have existed without leaving enough remains for humans to ever discover them. In modern oceans, enormous animals can still avoid human observation surprisingly often. Sperm whales dive thousands of feet into darkness humans rarely visit. Giant squid were largely creatures of myth until relatively recently in scientific terms. Even today, deep-sea cameras regularly capture organisms that appear almost unreal. If modern oceans still conceal massive life forms, despite satellites, sonar, and global shipping routes, then prehistoric oceans, vastly older and far less accessible, may have contained ecological mysteries we will never fully reconstruct. That uncertainty changes the emotional scale of the ancient sea. It stops feeling like a finished chapter in natural history and begins feeling more like a shadowed world only partially illuminated. The further you move into prehistoric oceans, the less human intuition seems to apply. Modern humans evolved primarily on open land under sunlight. Our instincts are not designed for deep water. We fear what we cannot see beneath us, because for most of evolutionary history, hidden water often meant danger. Ancient seas intensified that danger beyond anything humans ever experienced directly. The person dropped into one of those oceans would not merely encounter unfamiliar animals, they would enter an ecosystem where they occupied no meaningful place at all. No technology, no boats, no coast guard, no understanding of migration routes or hunting behavior, just endless water beneath a sky that would look familiar, while everything below the surface remained utterly foreign. Some prehistoric predators may have hunted by ambush from below, similar to modern crocodilians or certain sharks. Others likely pursued prey across long distances, using speed and endurance. Giant marine reptiles with massive eyes may have descended into darker depths where sunlight barely reached. In those depths, shape and scale become difficult to judge. A creature 20 or 30 feet long, emerging from black water, might remain invisible until the final seconds before impact. The ocean does not allow distance to feel safe in the same way land does. Sound travels differently underwater. Light disappears quickly. Orientation becomes unstable. And perhaps that is part of why prehistoric marine life still fascinates people so deeply today. Dinosaurs walked in front of us, at least in our imagination. But ancient sea predators approached from below, from darkness, from a world humans were never truly built to control. Even now, despite all modern technology, humanity remains surprisingly fragile at sea. Storms still sink ships. Currents still kill experienced divers. Entire aircraft disappear over open water and are never fully recovered. The ocean has always resisted complete human domination. Prehistoric oceans simply represented that reality in its most extreme form. A planet where the sea was not a route between civilizations, but an enormous living system ruled by creatures larger than anything most humans could psychologically process if they encountered them alive today. And as Earth continued changing through mass extinctions, shifting climates, and evolving ecosystems, those oceans would repeatedly create new giants, to replace the old ones. Some would resemble nightmares. Some would resemble monsters from mythology. And some would become so massive that even modern paleontologists occasionally struggle to believe they were real at all. Long before whales crossed the oceans in slow migrating giant pods, before dolphins learned to communicate through bursts of sound beneath the waves, another group of animals had already solved the problem of becoming masters of the open sea. They were not fish, they were not mammals. And despite how perfectly adapted they looked for ocean life, their ancestors once walked on land. The ichthyosaurs emerged during one of the most chaotic periods in Earth's history, shortly after the Permian mass extinction nearly erased complex life from the planet around 252 million years ago. Entire ecosystems collapsed. Oceans lost huge portions of their oxygen. Countless species disappeared forever. Yet out of that devastation came evolutionary opportunities so enormous that some surviving reptiles began moving into ecological roles left empty by extinction. Over millions of years, certain lineages drifted farther from shore, their bodies slowly reshaped by water itself, until they no longer resembled terrestrial reptiles at all. By the time the first true dinosaurs began appearing on land, the seas were already filling with sleek marine predators whose silhouettes would look strangely familiar to modern eyes. That familiarity is one of the most fascinating things about ichthyosaurs. If someone saw one alive from a distance, they might initially mistake it for a dolphin or small whale. They possessed long, streamlined bodies, dorsal fins, elongated snouts, and crescent-shaped tails built for speed in open water. But this resemblance was not because dolphins evolved from ichthyosaurs or inherited their design. In reality, these animals were separated by enormous evolutionary distance. One was a reptile lineage from the Triassic and Jurassic oceans. The other was a mammal lineage that would not fully return to marine life until much later. Yet both ended up arriving at surprisingly similar body structures, because physics tends to reward certain designs in fast-moving ocean predators. Scientists call this convergent evolution, but the term itself almost understates how strange the result really is. It means Earth independently created ocean torpedoes more than once. Different branches of life, separated by time and ancestry, discovered that streamlined bodies, powerful tails, and narrow skulls were simply among the most effective ways to hunt through open seas. In a sense, the ocean forced evolution toward efficiency. Water punished awkwardness. Only the most hydrodynamic forms survived long enough to dominate. Some ichthyosaurs remained relatively modest in size, hunting fish and squid through coastal waters. Others became gigantic. Shonisaurus, one of the largest known ichthyosaurs, may have reached lengths exceeding 50 feet, approaching the size of modern sperm whales. Another giant species called Shastasaurus may have grown even larger, depending on which fossil interpretations are accepted, though exact estimates remain debated because complete skeletons are rare. What makes these enormous marine reptiles so compelling is not only their size, but how early they appeared in Earth's recovery after mass extinction. Life rebounded with astonishing speed. Within tens of millions of years after one of the deadliest catastrophes in planetary history, the oceans were once again supporting massive apex predators, crossing prehistoric seas in search of prey. That rapid recovery challenges the common assumption that evolution always moves slowly and cautiously. Under the right environmental pressures, ecosystems can transform dramatically, and the Triassic oceans may have been among the most experimental ecosystems Earth ever produced. Some ichthyosaurs evolved eyes so large that paleontologists still struggle to fully explain them. The species Ophthalmosaurus possessed enormous eye sockets reinforced by rings of bony plates designed to stabilize the eyeball against pressure. Its eyes may have been among the largest relative to body size of any vertebrate known. This detail becomes more unsettling when considering what such eyes imply. Large eyes are often associated with environments where light is limited. Modern deep-diving predators like giant squid and sperm whales rely heavily on vision in dim waters. Certain ichthyosaurs may have hunted at depths where sunlight barely penetrated, descending into dark layers of the ocean filled with soft-bodied prey invisible near the surface. Imagine drifting through prehistoric black water with only fragments of filtered light above, while enormous reptiles scanned the darkness around you using eyes evolved specifically for low-light hunting. The ancient sea was not only dangerous at the surface, it likely extended vertically into deep ecosystems humans still poorly understand even now. Fossil evidence suggests many ichthyosaurs gave birth to live young rather than laying eggs on land. This adaptation reveals just how completely they had committed to marine existence. Unlike sea turtles, which still return to beaches to reproduce, ichthyosaurs appear to have severed nearly all ties to land entirely. Fossilized mothers have been discovered with embryos preserved inside their bodies, and in some remarkable specimens, babies are captured in the process of birth itself. One famous fossil shows a juvenile emerging tail first, likely an adaptation that reduced the risk of drowning during delivery underwater. That single detail transforms these creatures from monsters into fully realized animals shaped by millions of years of evolutionary refinement. They were not awkward reptiles experimenting with swimming. They were permanent citizens of the ocean. Entire generations lived and died without ever touching land. Yet, despite their success, much about ichthyosaur behavior remains uncertain. Scientists can estimate swimming speed from tail structure and muscle attachment. They can infer diet from stomach contents and tooth shape. But many aspects of their social behavior remain speculative. Did they travel in pods like dolphins? Did giant species migrate across oceans following prey routes? Were some capable of complex communication beneath the surface? Certain fossil sites containing multiple individuals together hint at social grouping, though interpreting behavior from fossils is always difficult. The ocean destroys evidence quickly. Bones scatter. Predators scavenge remains. Entire behaviors disappear without leaving physical traces. And so the prehistoric sea retains an eerie silence around many of its most important questions. One of the most intriguing mysteries surrounding ichthyosaurs is their eventual decline. For tens of millions of years, they thrived across Earth's oceans. They survived environmental shifts, changing climates, and competition from other marine predators. Then, gradually, during the later stages of the Cretaceous period, they disappeared entirely before the asteroid impact that ended the age of non-avian dinosaurs. Their extinction remains debated. Some researchers suggest changing ocean ecosystems disrupted the prey species they relied upon. Others point toward competition from emerging marine reptiles such as mosasaurs, or increasingly advanced fish species adapting to similar ecological niches. Climate changes and shifting ocean chemistry may also have played roles. There is no single, universally accepted explanation, which makes their disappearance strangely haunting. Creatures that once seemed perfectly adapted for marine dominance slowly faded from the oceans long before the world-ending catastrophe most people associate with prehistoric extinction. It is possible their specialized adaptations eventually became vulnerabilities once ecosystems changed beyond certain thresholds. Evolution creates efficiency, but extreme specialization can become dangerous when environments shift unexpectedly. What makes ichthyosaurs emotionally fascinating is that they feel uncannily modern despite belonging to a world unimaginably ancient. They occupied ecological roles humans instinctively recognize: fast pelagic hunters, deep divers, live-bearing marine predators crossing open water. In another timeline, if mass extinction events had unfolded differently, perhaps descendants of ichthyosaurs might still inhabit Earth's oceans today, alongside whales and sharks. The seas might contain intelligent marine reptiles, adapted across hundreds of millions of uninterrupted evolution. That idea remains speculative, of course, but it reveals something important about Earth's history. The dominance of mammals in modern oceans was not inevitable. Before whales ever evolved, another lineage had already become the giants of the sea. And the deeper scientists study prehistoric marine life, the clearer it becomes that Earth repeatedly experiments with similar solutions to survival. Different ages produce different rulers, but the ocean continually shapes them toward the same cold efficiency: speed, endurance, streamlining, sensory precision. Predators built not merely to survive water, but to disappear into it. In many ways, ichthyosaurs represent one of the clearest examples of how the sea changes life itself. Land animals entering marine environments gradually surrender features once essential for terrestrial existence. Legs transform into flippers, spines bend differently, breathing patterns change. Even birth adapts to the pressure and movement of water. The ocean does not compromise. It reshapes organisms completely or destroys them. And perhaps that is why ancient marine reptiles still feel so mysterious today. They remind us that evolution is not marching toward a final perfect form. It is responding endlessly to environments that never stop changing. The ichthyosaurs were once among the most successful animals on Earth. Entire oceans belonged to them. Yet, eventually, even they vanished, leaving behind only skeletons buried inside stone that was once seafloor. Today, when paleontologists uncover those fossils, high in mountains or dry deserts, there is something almost surreal about the realization that these landscapes were once deep underwater worlds ruled by creatures resembling prehistoric whales long before whales existed. The earth beneath our feet carries the remains of oceans that disappeared millions of years before humans arrived. And hidden inside those rocks is the memory of a time when massive reptilian hunters moved silently through ancient seas beneath skies no human eyes would ever witness. If the ichthyosaurs became the sleek, long-distance hunters of the prehistoric seas, then the pliosaurs were something far more brutal. They did not glide through the ocean like dolphins. They moved through it like armored ambush weapons built entirely around violence. Enormous heads, thick necks, massive jaws lined with conical teeth designed not for slicing, but for gripping prey so powerfully that escape may have become nearly impossible once the bite connected. In some species, the skull alone stretched close to 6 or 7 feet long, turning the front of the animal into a living trap capable of crushing bone, tearing flesh, and overpowering creatures already enormous by prehistoric standards. And unlike many marine predators that specialized in smaller prey or fast pursuit, pliosaurs appear to have occupied one of the most terrifying ecological roles imaginable. Apex hunters large enough to attack almost anything sharing their waters. The oceans of the Jurassic period were already crowded with marine reptiles, giant fish, ammonites, and early forms of fast-swimming predators. But pliosaurs evolved into something different. They were not merely participants in the ecosystem. In many regions, they may have stood at the very top of it. One of the strangest things about pliosaurs is how disproportionate they looked compared to modern marine animals. Their bodies often resembled oversized torsos powered by 4 muscular flippers, while the head appeared almost absurdly large. Modern evolution tends to favor streamlined efficiency, but pliosaurs seemed built around overwhelming force first and hydrodynamics second. Their skulls contained enormous attachment areas for jaw muscles, suggesting bite forces powerful enough to rival or exceed many predators alive today. Some paleontologists believe certain species may have generated one of the strongest bites in marine reptile history. And unlike sharks, whose teeth are often designed to cut chunks from prey, pliosaur teeth functioned more like giant spikes. Once embedded, those teeth could hold struggling animals with terrifying stability. Fossilized bite marks found on bones from other marine reptiles hint that these creatures did not hesitate to attack massive prey. In some prehistoric seas, survival may have depended less on avoiding one predator and more on avoiding becoming trapped inside a food chain where every large animal hunted every other large animal. Among the most famous pliosaurs is Leopleurodon, a name that became legendary partly because of documentaries that once exaggerated its size to almost mythical proportions. Early television portrayals suggested lengths exceeding 80 feet, transforming it into something close to a sea dragon from ancient mythology. More recent scientific estimates tend to place most known individuals closer to around 20 to 35 feet, depending on species and fossil interpretation, though even these revised measurements still describe an enormous predator, fully capable of dominating marine ecosystems. The exaggeration itself is interesting because it reveals how easily prehistoric oceans invite the imagination to expand beyond evidence. Marine fossils are often incomplete. A skull here, vertebrae there, fragments buried under cliffs or frozen rock layers. Unlike dinosaur skeletons found articulated in dry sediment, ocean predators are frequently reconstructed from scattered remains. This uncertainty creates space for speculation, and few creatures demonstrate that tension between science and imagination more clearly than the pliosaurs. Yet, even stripped of exaggeration, the reality remains intimidating enough. A predator with a skull larger than many adult humans, swimming silently through dark Jurassic water, does not require myth to become frightening. One species that genuinely may have approached extraordinary size was Kronosaurus, named after the titan Kronos from Greek mythology. Fossils discovered in Australia and South America suggest a marine predator with a broad skull and heavily built body, adapted for power rather than endurance migration. The oceans it inhabited during the Cretaceous period were warm, biologically rich, and filled with large prey animals. Kronosaurus likely hunted fish, turtles, squid-like cephalopods, and potentially other marine reptiles. Some fossilized stomach contents appear to support this wide-ranging diet. That detail matters because apex predators capable of consuming many different prey types often become ecologically resilient. Rather than depending on one food source, they dominate entire layers of the food web. In modern oceans, orcas occupy a somewhat comparable role in certain regions, hunting seals, fish, sharks, and even whales depending on the population. But the comparison only goes so far. Orcas are intelligent social mammals with complex communication systems. Pliosaurs were reptiles from a world operating under very different evolutionary pressures. Their intelligence level remains uncertain. Their social behavior remains almost entirely unknown. They may have been solitary hunters, moving through open water alone for most of their lives. If so, the ancient ocean would have felt even more unsettling. Enormous, silent predators appearing from darkness without warning or sound. The mechanics of pliosaur hunting continue to fascinate paleontologists because their anatomy suggests multiple strategies may have existed across different species. Some likely relied on sudden bursts of acceleration, using powerful flippers to lunge upward into prey schools or attack large animals from below. Others may have hunted more slowly through ambush near coastlines or deeper channels where visibility was limited. Their eye placement suggests strong forward vision useful for depth perception during attacks. Certain skull structures indicate the ability to withstand enormous stress during violent struggles with prey. In some fossils, broken teeth appear healed, implying these animals survived repeated combat with dangerous targets. The ocean during the Jurassic and Cretaceous periods may have resembled an endless battlefield, where even apex predators routinely suffered injuries. There is also evidence suggesting that some marine reptiles, including pliosaurs, may have attacked each other. Fossil bones carrying bite marks from large conical teeth hint at violent interactions between giant predators. Whether these encounters represented territorial combat, scavenging, or direct predation remains debated in many cases. But the existence of those wounds tells an important story about prehistoric oceans. These ecosystems were not stable, peaceful worlds where giant creatures drifted calmly beneath the waves. They were intensely competitive environments shaped by constant pressure. Large predators did not merely evolve impressive size for display. They evolved it because anything weaker risked becoming prey itself. Perhaps the most haunting aspect of pliosaurs is how little warning they may have given their victims. Water absorbs sound differently than air. Visibility fades rapidly with depth. Many marine hunters today rely on surprise because the ocean naturally conceals movement. A giant predator approaching beneath dark water could remain nearly invisible until the final moment of attack. Modern great white sharks already exploit this principle by striking upward from below with explosive speed. Now imagine a predator far larger, armed not with serrated slicing teeth, but with jaws built to seize and hold. Certain pliosaurs may have generated panic across entire ecosystems simply through their presence. Prey animals likely altered migration routes, feeding behavior, and breeding grounds to avoid regions dominated by large marine reptiles. The influence of apex predators extends far beyond the animals they directly kill. They shape the behavior of everything around them. One reason pliosaurs continue capturing public imagination is that they occupy an uncomfortable middle ground between recognizable biology and ancient nightmare. Unlike some prehistoric creatures that appear too alien to emotionally connect with, pliosaurs feel disturbingly plausible. Humans instinctively understand jaws, teeth, ambush predators. The fear they trigger is primal. Yet their scale pushes them beyond ordinary experience. A person encountering one in open water would likely have almost no chance of survival. Not because the predator was supernatural, but because the ocean itself removes human advantages. No footing, no visibility, no reliable escape direction. Even modern humans remain surprisingly helpless in deep water compared to marine predators evolved over millions of years specifically for that environment. There is another layer of mystery surrounding pliosaurs that scientists still debate quietly. Some fossil discoveries hint that certain marine ecosystems may have supported predator diversity far greater than once believed. Different species of giant hunters may have partitioned hunting zones by depth, prey type, or coastline geography in ways we only partially understand. In modern oceans, multiple apex predators can coexist by specializing differently. Sperm whales dive deep for squid. Orcas hunt cooperatively near the surface. Sharks patrol specific thermal layers. Ancient seas may have operated similarly, with pliosaurs dominating particular ecological niches, while other marine reptiles occupied neighboring ones. If true, some prehistoric oceans were not ruled by one giant predator, but by several simultaneously. That possibility transforms the ancient sea from a simple ecosystem into something far more dynamic and terrifying. Overlapping territories filled with competing monsters adapted for different styles of killing. Yet despite all their power, pliosaurs eventually disappeared. Their reign ended long before humans arrived to witness it. Climate shifts, changing prey populations, competition from emerging marine predators, and broader ecological transformations likely all contributed. As always in deep time, extinction rarely comes from a single cause alone. Dominance in one era does not guarantee survival in the next. The same evolutionary pressures that once created giant marine predators eventually erased them when oceans changed beyond what their specialized bodies could handle. And perhaps that is one of the deepest patterns hidden inside Earth's history. The planet continuously creates giants, then slowly removes them. Entire dynasties of apex predators rise and vanish, while the oceans remain. Today, when paleontologists reconstruct pliosaur skulls inside museums, there is often something almost disproportionate about them. The jaws seem too large, the teeth too thick, the head too heavily built to feel real. But those fossils are reminders that prehistoric oceans were not simply larger versions of modern seas. They were fundamentally different worlds, shaped by evolutionary experiments that no longer exist. And somewhere beneath the warm waters of the Jurassic, long before whales inherited the oceans, giant pliosaurs once moved through the darkness with enough force in their jaws to crush the bones of almost anything alive beside them. Near the very end of the age of dinosaurs, when the continents of Earth still looked unfamiliar and sea levels drowned enormous portions of the planet beneath warm inland oceans, a different kind of marine predator began taking control of the seas. The giant pliosaurs that once dominated earlier prehistoric oceans were mostly gone. Ichthyosaurs had already disappeared after millions of years ruling open waters. Ecological space had opened again, and evolution moved quickly to fill it. Out of that changing world emerged the mosasaurs, massive marine reptiles whose rise happened so late in Earth's prehistoric story that they were living only a few million years before the asteroid impact that would erase most large life on the planet. And unlike some earlier marine reptiles that evolved into sleek, whale-like shapes, mosasaurs retained something far more unsettling in their appearance. They looked less like ocean mammals and more like gigantic predatory lizards transformed by water into something monstrous. Their bodies stretched long and muscular through the sea, with powerful tails driving them forward in sudden bursts of speed. Their skulls carried rows of sharp, recurved teeth built for gripping slippery prey. Some species possessed double-hinged jaws that allowed them to swallow surprisingly large animals whole, a feature that immediately invites comparison to modern snakes. That comparison is not accidental. Mosasaurs were closely related to monitor lizards and snakes within the squamate reptile family tree, meaning that deep beneath all their marine adaptations remained the evolutionary blueprint of terrestrial reptiles. In a strange way, the oceans of the late Cretaceous became haunted by giant, sea-going versions of predatory lizards, creatures capable of growing over 40 feet long while patrolling warm, prehistoric seas already crowded with sharks, giant fish, ammonites, turtles, and other marine reptiles. The timing of their dominance makes them especially fascinating. Mosasaurs did not slowly rise over hundreds of millions of years. Their success appears relatively rapid in evolutionary terms. Within a surprisingly short geological window, they diversified into numerous species adapted for different hunting strategies and environments. Some were built for speed in open oceans. Others possessed crushing teeth capable of breaking armored prey. Certain smaller species may have hunted fish along coastlines and shallow reefs, while the largest forms became apex predators capable of attacking nearly anything sharing their ecosystem. The late Cretaceous seas may have represented one of the most intensely competitive marine environments in Earth's history. Unlike earlier oceans, dominated by a handful of giant predator lineages, these waters supported multiple powerful hunters simultaneously. Sharks were evolving into increasingly advanced forms. Large predatory fish still roamed open waters, and above them all moved giant mosasaurs, whose flexibility, speed, and feeding adaptations allowed them to exploit a wide range of prey. One reason mosasaurs feel so unnerving compared to many prehistoric animals is that their anatomy still looks biologically recognizable. Their skulls resemble exaggerated versions of predators humans instinctively fear. Long jaws, forward-facing attack posture, teeth curved backward to prevent escape. Unlike giant herbivorous dinosaurs, whose size can almost feel abstract, mosasaurs project direct predatory intent even through fossils. Paleontologists studying their skull mechanics discovered that certain species possessed kinetic jaws with flexible joints, allowing sections of the mouth to move independently during feeding. This likely helped them manipulate struggling prey deeper into the throat, somewhat similar to mechanisms seen in snakes today. Combined with an additional row of teeth on bones located toward the roof of the mouth, these reptiles may have been extraordinarily effective at preventing prey from escaping once bitten. In dark water, against a creature that large, even a single mistake likely became fatal. Fossil evidence suggests mosasaurs were not selective hunters. Stomach contents and bite marks indicate diets including fish, seabirds, turtles, ammonites, sharks, and even other mosasaurs. Some specimens appear to show signs of violent combat between giant individuals. Broken bones healed during life hint at attacks survived against dangerous opponents. Bite marks on skulls and vertebrae suggest direct conflict may not have been uncommon. Whether these encounters represented territorial disputes, competition over food, scavenging, or outright cannibalism remains debated depending on the fossil case. But the broader picture emerging from the late Cretaceous oceans is difficult to ignore. These seas were filled with large predators, constantly overlapping in territory and prey choice. Survival depended on speed, aggression, and adaptability. The oceans had become ecosystems where even apex predators were never entirely safe from each other. One particularly haunting detail about mosasaurs is how completely they adapted to life in water despite descending from terrestrial ancestors. Early relatives likely spent time near shorelines, much like modern marine iguanas or semi-aquatic lizards. But later mosasaurs evolved bodies fully committed to ocean existence. Their limbs transformed into flippers. Their tails developed crescent shapes optimized for propulsion. Bone structures suggest many species were strong swimmers, capable of sustained movement across open seas rather than merely coastal ambush hunters. Some paleontologists even suspect certain mosasaurs regulated body temperature more efficiently than traditional cold-blooded reptiles, though exactly how remains uncertain. If true, this may have helped them maintain active hunting lifestyles across wider ocean regions. The deeper researchers examine these animals, the harder it becomes to categorize them using simple modern comparisons. They were not exactly giant crocodiles, not sea snakes, not marine dinosaurs. They represented a unique experiment in marine predation that emerged late, spread rapidly, and vanished almost as suddenly as it appeared. Perhaps the most famous mosasaur of all is Mosasaurus itself. First discovered in limestone quarries near the Meuse River in Europe during the late 18th century. In fact, its discovery became historically important because it occurred before dinosaurs were formally recognized by science. At the time, naturalists struggled to understand what exactly they were looking at. Some believed the skull belonged to a giant crocodile. Others imagined unknown sea creatures unlike anything living. The fossil challenged humanity's understanding of Earth's history before the concept of prehistoric worlds fully existed in public thought. In many ways, mosasaurs helped introduce the idea that entirely different ecosystems once ruled the planet long before humans arrived. That intellectual shock still lingers today. Standing beside a reconstructed mosasaur skeleton in a museum does not simply feel like observing an extinct animal. It feels like confronting evidence of another version of Earth. A world where giant reptiles ruled warm inland seas stretching across continents, now dry and populated by cities. One of the most intriguing aspects of mosasaur evolution is that they rose during a period when Earth itself was becoming unstable. Sea levels fluctuated, climate patterns shifted, ecosystems grew increasingly complex and pressured. Yet, rather than collapsing immediately, life intensified. The late Cretaceous appears almost overloaded with biological specialization. Giant herbivorous dinosaurs thundered across floodplains on land, while giant marine reptiles dominated beneath the oceans. Flowering plants spread rapidly, insects diversified, mammals quietly evolved in the background. Earth before the extinction event was not a dying world. It was extraordinarily alive. And that makes what happened next even more disturbing. Because while mosasaurs ruled the seas with terrifying efficiency, the planet was already approaching one of the most catastrophic turning points in its history. Around 66 million years ago, an asteroid roughly several miles wide struck near modern-day Mexico with unimaginable force. The immediate destruction alone was devastating. Shockwaves, firestorms, tsunamis, earthquakes. But the longer-term effects may have been even worse. Dust and aerosols thrown into the atmosphere likely blocked sunlight, disrupting photosynthesis across land and sea. Food chains collapsed from the bottom upward. In oceans, plankton populations appear to have suffered massive decline, triggering cascading ecological failures throughout marine ecosystems. Large predators like mosasaurs depended on stable food webs supporting immense amounts of prey biomass. Once those systems destabilized, survival became increasingly difficult. The terrifying giants ruling the late Cretaceous oceans vanished along with the non-avian dinosaurs on land. And yet, even in extinction, mosasaurs left mysteries behind. scientists still debate exactly how fast their collapse occurred after the impact. Some fossil evidence suggests marine ecosystems may have experienced complex regional survival patterns before total extinction. There are ongoing discussions about how specialized different mosasaur species truly were, and whether some lineages were already declining before the asteroid struck. The fossil record near mass extinction boundaries is notoriously difficult to interpret cleanly. Geological layers compress enormous spans of time into thin sections of rock. Entire populations can disappear from evidence long before their actual extinction, or seem to persist longer, depending on preservation conditions. The result is a haunting uncertainty around Earth's final age of giant marine reptiles. We know they vanished. We know the world changed forever. But the precise final chapters remain blurred beneath millions of years of geological silence. What remains undeniable is that mosasaurs represented one of the last great dynasties of prehistoric sea predators before the modern age began. They arrived late, evolved rapidly, and transformed the oceans into ecosystems dominated by giant reptilian hunters only shortly before catastrophe erased them completely. And perhaps that timing is why they feel so cinematic even today. They were not ancient relics fading quietly into extinction over endless ages. They were apex predators at the height of their success when the sky itself suddenly turned against the planet. In the final days before impact, giant mosasaurs still cruised through warm prehistoric oceans beneath sunsets no creature could understand would soon disappear forever. For millions of years, the oceans of the late Cretaceous had felt unstoppable. Giant mosasaurs hunted through warm inland seas. Sharks cruised beneath enormous schools of fish. Ammonites drifted through open water in numbers so vast they became one of the foundations of marine food chains. Entire ecosystems had evolved into astonishingly complex webs of predators and prey, balanced across a planet that, despite its violence, remained biologically rich beyond anything most humans could imagine. From the surface, Earth would have appeared alive everywhere. Dense forests stretched across continents. Rivers carried nutrients into shallow seas. Reptilian giants still ruled both land and water. And because life had already survived countless catastrophes before, nothing about the planet would have suggested that one particular day would become one of the darkest turning points in the history of the oceans. Then somewhere above Earth's atmosphere, moving faster than a rifle bullet and carrying more destructive energy than the combined nuclear arsenals of the modern world, an asteroid roughly 6 to 9 miles wide entered the sky. The object itself was not enormous compared to planets or moons, but speed transformed it into something catastrophic. When it struck near what is now the Yucatan Peninsula around 66 million years ago, the collision released energy so extreme that it permanently altered life on Earth in ways still visible in the fossil record today. What happened next likely unfolded too quickly for any large creature to comprehend. The first moments alone would have been apocalyptic. Rock vaporized instantly. Shockwaves raced across continents. Earthquakes rippled outward with unimaginable force. Debris blasted into the upper atmosphere. And in coastal regions surrounding the impact, walls of water rose high enough to erase entire marine ecosystems within hours. Some tsunami models suggest waves may have reached heights difficult to fully visualize, moving across ancient seas with enough energy to tear apart shorelines and scatter marine animals far inland. But the terrifying part of the extinction event was not merely the violence of the impact itself. It was what happened afterward, when the oceans slowly began losing the systems that kept them alive. At first glance, water may seem protected from atmospheric catastrophe. Creatures deep beneath the surface would not experience firestorms directly. Entire marine regions existed thousands of miles from the impact site. Yet oceans depend completely on energy flowing down from sunlight. The moment Earth's atmosphere filled with dust, ash, sulfur compounds, and vaporized material, sunlight reaching the planet's surface likely dropped dramatically. Some scientists believe the skies may have darkened globally for months or even years, depending on atmospheric models. Photosynthesis collapsed across huge portions of Earth's ecosystems. On land, forests withered. But in the oceans, the consequences became even more profound, because marine food chains begin with microscopic organisms near the surface. Tiny plankton, almost invisible individually, support entire ocean ecosystems by converting sunlight into biological energy. When those plankton populations crashed, the effects rippled upward through every level of marine life. Small fish lost food. Larger predators lost prey. Giant marine reptiles, dependent on stable ecosystems, suddenly faced oceans where the energy foundation itself had started disappearing. The extinction was not simply about giant predators dying. It was about the oceans slowly running out of life to sustain them. One of the most haunting aspects of this event is that the seas may not have become dramatically violent everywhere at once. In many regions, the water may have looked deceptively calm. Waves still moved. Tides still shifted along coastlines. But beneath the surface, ecosystems were beginning to unravel. Creatures adapted to abundance suddenly faced scarcity. Predators evolved for rich food chains entered collapsing environments where migration routes no longer worked and prey populations declined unpredictably. Imagine a giant mosasaur crossing ancient seas, searching for familiar hunting grounds, only to find emptier water year after year. Some marine species likely died rapidly after the impact. Others may have survived for generations before finally disappearing as ecosystems continued destabilizing. The fossil record compresses time in ways that make extinction appear sudden. But in reality, for many animals, the end may have unfolded as a long ecological collapse rather than a single moment of destruction. There is growing evidence that ocean chemistry itself changed dramatically after the impact. Acidification may have spread through marine environments as atmospheric compounds dissolved into seawater. Organisms relying on calcium carbonate shells, including ammonites and many plankton species, became especially vulnerable. Once these foundational species disappeared, food webs weakened even further. And because oceans are interconnected systems, local collapses could cascade across enormous distances. Regions untouched directly by tsunamis or firestorms still suffered because marine ecosystems depend on global circulation patterns carrying nutrients, oxygen, and migrating life forms across the planet. The oceans of the late Cretaceous had evolved into highly productive ecosystems, but that complexity may also have made them fragile. Once enough foundational species disappeared simultaneously. One detail often overlooked is that freshwater and deep-sea environments may have experienced the catastrophe differently. Certain deep ocean regions possibly acted as partial refuges where temperature fluctuations and surface collapse were buffered temporarily by depth. Some bottom-dwelling organisms survived. Sharks survived. Crocodilians survived. Various fish lineages survived. Meanwhile, giant marine reptiles like mosasaurs vanished entirely. Why some groups endured while others disappeared remains one of the most important questions in extinction science. Size alone does not explain survival. Neither does intelligence or physical strength. In many cases, adaptability appears more important than dominance. Smaller animals with flexible diets, faster reproduction, or lower energy requirements often outlast specialized giants during ecological collapse. The creatures ruling the oceans before the impact were extraordinarily successful within stable ecosystems. But extreme specialization can become dangerous when environments change faster than evolution can respond. Some scientists have even suggested that certain marine ecosystems were already under environmental stress before the asteroid arrived. Massive volcanic eruptions in what is now India, known as the Deccan Traps eruptions, released enormous amounts of gas and lava over extended periods around the same time frame. These eruptions may have altered climate systems, ocean chemistry, and atmospheric conditions before the impact event intensified everything catastrophically. The relationship between volcanism and the asteroid extinction remains debated in terms of relative contribution, but many researchers suspect both factors interacted in complex ways. If so, the end of the Cretaceous oceans was not caused by one isolated disaster alone, but by overlapping environmental crises striking ecosystems already under pressure. That possibility changes the emotional tone of the extinction entirely. Rather than a perfect world suddenly destroyed in a single afternoon, Earth may have been entering a period of increasing instability before the final blow arrived from space. Yet, even amid collapse, life did not fully disappear. That may be the strangest part of Earth's history. The oceans had endured multiple mass extinctions before the dinosaurs ever existed. Entire marine dynasties had already risen and vanished across hundreds of millions of years. And somehow, even after this catastrophe, enough organisms survived to rebuild marine ecosystems once again. Tiny fish endured in scattered refuges. Sharks persisted through deep evolutionary resilience. Early mammals survived on land. Birds descended from surviving dinosaur lineages continued into the modern world. The oceans became quieter after the extinction, but they did not become empty. They entered a long recovery process that would eventually produce entirely new rulers of the sea. Whales had not evolved yet. Modern dolphins did not exist. The marine world humans recognize today was still far away. But the extinction created ecological openings where future life would eventually expand. The silence following the catastrophe may have lasted millions of years in evolutionary terms. A planetary pause after ages dominated by giant reptiles. When paleontologists study sediment layers marking the extinction boundary, they often describe it as a line separating two completely different Earths. Below the layer lie the remains of ammonites, giant marine reptiles, and ecosystems that had ruled for millions of years. Above it, those creatures are gone. Entire branches of life vanish abruptly from the fossil record. The oceans after the impact were biologically diminished compared to what came before. And perhaps that is the most unsettling realization hidden inside this ancient catastrophe. The giant predators dominating prehistoric seas did not lose because they became weak. They lost because the systems supporting them collapsed underneath their feet or beneath their fins. Earth does not promise permanence to any species, no matter how successful it appears. Entire worlds can disappear while the planet itself keeps moving forward. And somewhere in those darkened, post-impact oceans, as food chains failed and ancient seas grew quieter, the last mosasaurs likely swam through waters that no longer resembled the world their ancestors had conquered. Long after the giant marine reptiles vanished from Earth's oceans, the seas slowly rebuilt themselves into something different. The age of reptiles gave way to the rise of mammals. Modern fish lineages expanded, and new predators evolved into ecological spaces once ruled by mosasaurs and pliosaurs. For millions of years, the oceans recovered from the catastrophe that ended the dinosaurs, becoming increasingly recognizable to modern eyes. Early whales began appearing. Seals and seabirds evolved along coastlines. Coral ecosystems spread through warmer waters. At first glance, it may seem as though the truly monstrous era of marine life had ended forever. But evolution was not finished creating giants. Somewhere between roughly 23 and 3.6 million years ago, during the Miocene and Pliocene epochs, a predator emerged that would eventually become one of the most famous animals in Earth's history, despite the fact that no human being ever saw it alive. Unlike the reptilian hunters that ruled prehistoric seas before the asteroid impact, this new apex predator belonged to a lineage still haunting modern oceans today. It was a shark. And not simply a large shark, but a creature so enormous that even modern great whites begin to look strangely small in comparison. The Megalodon did not resemble a sea monster invented by mythology. That is part of what makes it so unsettling. It looked plausible, real. A shark enlarged beyond modern expectation, but still shaped according to rules human instincts immediately recognize. Torpedo body, massive jaws, endless rows of serrated teeth, black eyes adapted for open water hunting. There is something psychologically different about gigantic sharks compared to gigantic reptiles. Reptiles can feel ancient and alien. Sharks feel current, familiar. Human beings still swim in oceans with their descendants. And because sharks already occupy such a primal place in human fear, scaling one upward to impossible proportions creates a predator that feels disturbingly believable. Fossil evidence suggests the largest Megalodon individuals may have reached lengths around 50 to possibly over 60 feet, depending on the reconstruction model used, though exact size estimates remain debated because sharks are primarily made of cartilage rather than bone. leaving behind incomplete fossil records. Most reconstructions rely heavily on teeth, vertebrae, and comparisons with modern shark anatomy. That uncertainty has fueled endless fascination. Every newly discovered tooth invites new size calculations. Every vertebra changes estimates slightly. Yet even the most conservative scientific interpretations describe an animal vastly larger than the largest recorded great white sharks alive today. And unlike many prehistoric predators known only from scattered fossils, Megalodon teeth are surprisingly common in certain regions. Fossil hunters still uncover them along beaches, cliffs, riverbeds, and ocean sediments around the world. Some are larger than a human hand, their serrated edges preserved across millions of years. Holding one creates a strange emotional reaction because it feels instantly understandable. This was not an abstract giant hidden in fragmented skeletons. It was a shark large enough to bite whales. That realization alone transforms the ocean into something colder. One of the reasons Megalodon became so successful was timing. The Miocene oceans were rich with marine mammals, especially early whales, diversifying into enormous numbers and ecological varieties. Ancient seas contained slow-moving baleen whales, smaller toothed whales, seals, dolphins, and other marine mammals that represented dense concentrations of calories for large predators. Megalodon evolved into an ecosystem where massive prey already existed in abundance. Some paleontologists believe its rise was directly tied to the expansion of whale populations across global oceans. The predator and prey relationship may have escalated over millions of years in an evolutionary arms race. As marine mammals grew larger and migrated farther, sharks capable of exploiting those prey sources gained advantages. Eventually, Earth produced a shark powerful enough to attack animals weighing dozens of tons. Fossilized whale bones carrying enormous bite marks provide some of the strongest evidence for this relationship. Certain specimens reveal healed injuries, suggesting some whales escaped attacks and survived encounters with giant sharks. Others show catastrophic damage, likely caused during fatal predation events. In some cases, bite patterns indicate targeted attacks on flippers, tails, or chest regions, strategies that would disable large marine mammals before killing them. Modern great whites already use similar tactics against seals and whales. Megalodon may have operated according to the same fundamental logic, simply on a scale almost difficult to emotionally process. The mechanics of its bite remain one of the most discussed aspects of the animal. Based on jaw reconstructions and muscle modeling, some scientists estimate Megalodon possessed one of the strongest bite forces ever produced by any vertebrate. Powerful enough not merely to cut flesh, but to crush bone. That detail matters because hunting whales is different from hunting fish. Marine mammals are large, muscular, intelligent, and capable of long-distance escape. A predator targeting them must inflict devastating damage quickly enough to prevent prolonged pursuit across open oceans. Megalodon appears to have solved that problem through overwhelming force. Its jaws likely functioned less like surgical tools and more like industrial crushing mechanisms designed to incapacitate enormous prey rapidly. Yet, despite its terrifying image, Megalodon was also a product of highly specific environmental conditions. Giant predators do not emerge randomly. They require stable food webs, capable of supporting massive energy demands. A shark that large needed immense quantities of prey across vast territories. It likely traveled enormous distances through warm coastal and open ocean environments, following whale migrations and productive feeding zones. Some fossil evidence suggests nursery areas existed in shallow, warmer waters where juvenile megalodons may have grown relatively protected from larger predators. That detail changes the emotional picture slightly. Even the most terrifying predator on Earth once began as a vulnerable juvenile, navigating dangerous oceans filled with larger hunters. The sea does not grant safety permanently to anything. One of the most fascinating questions surrounding Megalodon is coloration. Because soft tissue rarely fossilizes, scientists cannot know exactly what these sharks looked like in life. Many reconstructions portray them similarly to great whites, with countershaded gray and white coloration, a common adaptation among open water predators. But this remains speculative. It is entirely possible Megalodon carried darker coloration, different patterns, or adaptations unlike modern sharks. The uncertainty leaves space for imagination without fully abandoning scientific realism. In some ways, Megalodon occupies a perfect balance between evidence and mystery. Enough fossils exist to confirm its reality beyond doubt, but not enough to remove every unanswered question. That uncertainty partly explains why it continues dominating documentaries, movies, and public imagination decades after becoming scientifically famous. There is also ongoing debate regarding exactly how Megalodon hunted. Some researchers envision high-speed ambush attacks, similar to modern great whites, breaching upward into prey. Others argue its enormous size may have favored slower but massively powerful attacks focused on disabling large whales through repeated bites. Water temperature likely influenced its range as well. Certain studies suggest Megalodon preferred warmer oceans and may have avoided colder polar waters, though migrating prey could still have drawn it across huge distances seasonally. Every new fossil discovery slightly reshapes these interpretations. Paleontology often works through fragments and probabilities rather than certainty. The deeper scientists investigate ancient oceans, the clearer it becomes that prehistoric ecosystems were dynamic, changing systems filled with behaviors difficult to preserve in stone. Perhaps the most persistent fascination surrounding Megalodon is the question people continue asking despite overwhelming scientific skepticism. Could it still exist somewhere in the deep ocean? The idea survives partly because the sea itself remains mysterious. Human beings have explored only a fraction of Earth's deep oceans in detail. Strange species are still discovered regularly. Giant squid avoided direct observation for centuries, despite becoming legendary in sailor folklore. Combined with the sheer scale of the ocean, these realities allow imagination to keep the Megalodon alive culturally. But from a scientific perspective, evidence strongly indicates extinction. An apex predator of that size would require enormous food resources and likely leave far more physical evidence if living populations still existed today, whale carcasses would show distinct bite patterns. Modern oceans are heavily monitored through shipping, sonar, fisheries, and satellite observation. Additionally, many scientists believe cooling oceans during the Pliocene played a major role in Megalodon's extinction. As global climates shifted and colder waters expanded, marine ecosystems changed dramatically. Whale migration patterns altered. Some prey species declined or adapted differently. New predators, such as early orcas, emerged, hunting cooperatively and potentially competing with juvenile megalodons for resources. A giant warm water shark, specialized for massive prey, suddenly faced an ocean becoming less favorable for its survival strategy. In a strange way, Megalodon may have fallen victim to the same pattern that ended so many giant predators before it. Specialization creates dominance during stable conditions, but environmental change punishes dependence on narrow ecological advantages. The oceans that once supported Megalodon no longer existed in the same form. And slowly, the giant shark disappeared. Yet unlike mosasaurs or pliosaurs, Megalodon feels closer to modern reality, not just in time, but psychologically. The oceans humans swim in today are descendants of the same oceans it once ruled. Early human ancestors may have existed while the last megalodons still hunted offshore. That overlap creates an eerie sensation. This was not a creature from a completely alien Earth beneath unfamiliar stars. It was a shark, moving through oceans that already looked broadly recognizable, stalking whales beneath coastlines that would one day become human civilizations. Somewhere in the ancient Pacific or Atlantic, giant shadows, longer than many boats alive today, once crossed beneath waves carrying enough force in their jaws to shatter the skeletons of whales. And for millions of years, they were among the undisputed rulers of the sea. Even after everything humanity has built, satellites orbiting Earth, submarines descending miles beneath the surface, global shipping routes crossing every ocean every day, the deep sea remains one of the least understood environments on the planet. That fact alone continues feeding one of the oldest and most persistent questions humans ask about the ocean. Could enormous, unknown creatures still be hiding somewhere below? Not prehistoric reptiles surviving unchanged for millions of years, exactly as movies often imagine, but genuinely large organisms that science has either barely documented or not discovered yet. The reason this question refuses to disappear is because the ocean constantly gives humanity just enough mystery to keep certainty out of reach. Every few years, strange footage emerges from deep-sea expeditions. A squid larger than expected, a translucent predator drifting through darkness, an eel-like creature with jaws that barely resemble anything familiar. Sometimes, researchers capture sounds they cannot immediately identify. Sometimes, deep-water species appear on camera for the first time, despite existing unnoticed beneath humanity for centuries. And because the deep ocean is so enormous, so dark, and so physically hostile, people instinctively wonder what else might still be down there beyond the limits of observation. The scale of the unexplored ocean is difficult to emotionally process. More than 80% of Earth's oceans remain poorly mapped or unexplored in detail. Entire mountain ranges larger than the Rockies stretch across the seafloor. trenches descend deeper than Mount Everest is tall. Sunlight disappears almost completely within the upper few hundred meters of water, leaving the overwhelming majority of ocean volume in permanent darkness. Pressure increases so dramatically with depth that many deep-sea creatures would die instantly if brought to the surface too quickly. Human beings evolved under sunlight on dry land, and even modern technology struggles to function reliably in the deepest marine environments. A remotely operated vehicle descending several miles into the abyss enters a world colder than most polar winters, where visibility is limited to narrow beams of artificial light cutting through black water that has remained untouched by sunlight for millions of years. In that darkness, scale becomes difficult to judge. Distance loses meaning. A creature approaching from beyond the edge of the light may remain invisible until it is already near the camera. And unlike terrestrial ecosystems, where large animals often leave tracks, sounds, carcasses, or visible movement across landscapes, the ocean conceals evidence extremely well. Bodies sink. Scavengers erase remains rapidly. Vast regions exist where almost nothing reaches the surface. This concealment is one reason giant squid remained partly legendary for so long, despite being real animals. Sailors described enormous tentacled creatures centuries before science fully documented them. For generations, stories of sea monsters and giant cephalopods drifted between folklore and dismissed superstition. Yet modern biology eventually confirmed that colossal squid and giant squid truly exist, capable of reaching astonishing lengths in deep ocean environments. Even today, live observations remain relatively rare because these animals inhabit depths difficult for humans to study continuously. That history matters because it proves something important. The ocean has hidden genuinely large creatures from science before. However, that truth also creates a dangerous temptation to assume every mystery must conceal a monster. Modern marine biology operates in tension between humility and skepticism. Scientists understand the ocean remains deeply unexplored, but they also recognize that ecosystems obey physical and biological limits. A massive undiscovered predator would require food, breeding populations, ecological space, and evidence. The larger the animal, the harder it becomes to remain completely hidden indefinitely. This is where conversations about surviving megalodons often emerge. Popular culture loves the idea that giant prehistoric sharks still cruise the deepest trenches beyond human detection. At first glance, the theory feels emotionally plausible because the ocean already appears mysterious. But biologically, the evidence strongly argues against it. Megalodon was likely a coastal and open-water apex predator, dependent on enormous prey populations such as whales. Modern oceans are heavily monitored through fisheries, sonar systems, satellite tracking, whale research, submarine cables, and commercial shipping. A breeding population of giant sharks, dozens of feet long, would almost certainly leave physical traces: carcasses, feeding evidence, distinct bite marks, or reliable sightings supported by biological data. Deep trenches alone could not sustain large populations of gigantic, warm water predators indefinitely, because food availability becomes increasingly limited with depth. The abyssal ocean is not empty, but it is energetically sparse compared to productive coastal ecosystems. Yet, even if giant prehistoric predators are gone, the deep ocean still contains creatures capable of triggering profound unease. Some deep-sea fish possess enormous mouths and expandable stomachs, allowing them to consume prey nearly their own size, because meals are so rare in the abyss. Certain squid species drift through darkness with eyes adapted to detect tiny flashes of bioluminescence from far away. Giant isopods resembling armored alien insects crawl across seafloors thousands of feet below the surface. Frilled sharks retain body structures so ancient that they appear almost prehistoric compared to modern sharks. In many ways, the deep ocean already looks closer to another planet than to the shallow blue waters humans associate with beaches and coastlines. And unlike dinosaurs, these creatures are alive right now, beneath modern ships crossing overhead, unaware of what exists below them. One reason deep-sea gigantism occurs at all remains partly mysterious. Certain abyssal species grow surprisingly large compared to shallow water relatives. Giant squid, Japanese spider crabs, and oversized amphipods all hint at environmental pressures that can favor increased size in deep marine ecosystems. Some theories suggest colder temperatures, slower metabolisms, or unique ecological conditions contribute to this phenomenon, though explanations vary depending on species. The result is unsettling because it means the deep sea does not necessarily push life towards smallness alone. Under certain conditions, it can still produce giants. Not necessarily city-destroying monsters, but organisms large enough to remind humans that the ocean remains evolutionarily creative in ways we still poorly understand. Strange acoustic events have also fueled public fascination with hidden marine giants. One famous example is the bloop, an ultra-low frequency underwater sound detected in the Pacific Ocean in 1997. At first, the sound's immense volume and unusual characteristics led to speculation about unknown biological sources. Some people imagined gigantic, undiscovered animals producing calls larger than any known whale. Eventually, scientists concluded the sound was most likely caused by ice quakes and shifting Antarctic ice, rather than a living creature. But the emotional impact lingered, because for a brief moment, humanity confronted the possibility that something massive and unknown might exist beneath the ocean, beyond explanation. Similar stories repeat often in marine science. Unidentified sounds, brief sightings, blurry footage, mysterious scars on whales. Most eventually receive ordinary explanations or remain unresolved due to limited data rather than evidence of monsters. Yet each mystery reinforces the same deeper truth. Humans remain psychologically uncomfortable with how little of the ocean we truly control or understand. There is also an evolutionary reason deep water frightens people so effectively. Human vision depends heavily on light and distance recognition. The deep ocean removes both. In darkness, the brain struggles to predict danger. We instinctively fear environments where threats can approach invisibly from below. Prehistoric marine predators likely amplified those instincts for millions of years before humans ever evolved. Even modern sharks trigger disproportionate fear compared to statistically greater dangers because water conceals movement until the final moment. The deep sea represents the ultimate extension of that uncertainty, a place where almost anything could exist just beyond visibility. And while science strongly rejects many sensational monster theories, it simultaneously confirms that the ocean still contains biological surprises. New species are discovered regularly. Some lineages previously thought extinct have reappeared unexpectedly, such as the coelacanth, a fish once believed gone for over 60 million years before living individuals were found in the 20th century. Discoveries like that permanently changed how people think about the ocean. They proved extinction in the fossil record does not always mean absolute disappearance from reality. Still, there is an important distinction between surviving ancient fish hiding in isolated habitats and giant apex predators secretly ruling modern oceans. Biology places constraints on what ecosystems can support. The deeper researchers study marine food webs, the clearer those constraints become. But perhaps the most fascinating possibility is not that gigantic prehistoric monsters survived unchanged into the present. It is that the deep sea may contain forms of life humans have not yet imagined properly because our assumptions remain too shaped by surface ecosystems. Deep-water organisms often evolve toward appearances and behaviors that seem almost impossible when viewed through terrestrial expectations. Transparent bodies, bioluminescent organs, needle-like teeth, slow drifting movement through near-freezing darkness. The abyss rewards strategies very different from those familiar on land. Somewhere in that vast black water, there are almost certainly species still unknown to science. Some may be small. Some may be larger than expected. Some may already have brushed against submarine cameras before vanishing back into darkness. And perhaps that uncertainty itself is what continues pulling human imagination toward the ocean again and again. Because even in the modern world, after centuries of exploration, there are still places beneath the sea where humanity's knowledge fades into shadow. And beyond that shadow, the possibility of something enormous never disappears completely. One of the strangest patterns hidden inside Earth's history is that the oceans repeatedly create giants. Not once, not twice, but over and over again across entirely different eras, involving completely unrelated groups of animals. Giant armored fish appeared hundreds of millions of years ago, before dinosaurs even existed. Then came enormous marine reptiles during the age of dinosaurs. Later, gigantic sharks evolved into apex predators large enough to hunt whales. Eventually, modern oceans produced blue whales, the largest animals known to have ever lived anywhere on Earth. The details changed each time, but the pattern remained remarkably consistent. Whenever conditions allowed it, the sea pushed life toward immense scale. that raises a question deeper than simple curiosity about monsters. Why does the ocean keep producing creatures so much larger than most life on land? Why did evolution repeatedly favor gigantic marine animals across completely different branches of the tree of life? The answer appears to lie partly in physics itself. Water changes the rules of survival in ways that land never can. On land, gravity constantly fights size. Every additional pound of body mass must be supported by bones, muscles, joints, and circulatory systems strong enough to resist collapse under their own weight. A giant terrestrial animal faces enormous structural stress simply by standing still. This is one reason even the largest dinosaurs required specialized body designs with thick, pillar-like legs and carefully balanced movement. But underwater, buoyancy counteracts much of gravity's force. Water physically supports mass. A creature weighing dozens or even hundreds of tons can move through the ocean with a grace impossible on land, because its body is partially lifted by the surrounding environment. The sea essentially allows evolution to experiment with size more freely. A blue whale would collapse under its own weight if stranded on shore, yet underwater it moves with astonishing fluidity despite outweighing nearly every land animal that has ever existed. That single physical difference transformed the oceans into Earth's greatest laboratory for gigantism. Yet, buoyancy alone does not explain everything. Gigantic marine life also requires enormous energy. An ocean filled with giant predators cannot exist unless lower levels of the food chain produce staggering amounts of biological productivity. During several prehistoric periods, Earth's oceans appear to have become exceptionally productive ecosystems. Warm climates, high sea levels, nutrient-rich currents, and extensive shallow seas may have created marine environments capable of supporting massive populations of prey animals across huge geographic regions. In some prehistoric eras, continents were arranged differently, altering ocean circulation patterns in ways that potentially increased nutrient mixing and biological abundance. Warm, shallow inland seas spread across continents, creating enormous breeding grounds for fish, cephalopods, and marine reptiles. These ecosystems functioned almost like giant biological engines, continuously generating food for larger predators higher in the chain. The result was an escalating evolutionary system where size itself became advantageous. If prey animals grew larger, predators evolved larger bodies to hunt them more effectively. If predators became more powerful, prey species adapted through speed, armor, or increased body mass. Over millions of years, these pressures could create ecosystems where gigantism no longer represented an exception, but a stable survival strategy. In many prehistoric oceans, being enormous may have actually reduced vulnerability. Large marine animals face fewer predators once they pass certain size thresholds. Modern orcas rarely attack full-grown blue whales because the risk becomes too high relative to the reward. Similarly, giant prehistoric predators may have occupied ecological positions where almost nothing could threaten healthy adults. Gigantism can therefore function both offensively and defensively. Bigger bodies store more energy, travel farther, regulate heat more efficiently in cold water, and intimidate competitors. But gigantism also creates dependency. Large animals require huge territories and constant access to food. The same evolutionary advantages that allowed giants to dominate stable ecosystems often make them fragile when environments suddenly change. This pattern appears repeatedly throughout Earth's history. Giant marine reptiles vanished after ecological collapse. Megalodon disappeared as oceans cooled and food systems shifted. Gigantism works extraordinarily well until the planet itself changes the rules. One particularly fascinating aspect of marine gigantism is that it evolved independently multiple times in predators and filter feeders alike. Some giants hunted actively, like pliosaurs and Megalodon. Others evolved into enormous, peaceful feeders, consuming tiny organisms from the water itself, like modern baleen whales. This difference reveals something important about the ocean. It concentrates energy in ways land ecosystems rarely do. Massive schools of fish, swarms of krill, plankton blooms stretching for miles. Marine ecosystems can support feeding strategies impossible in most terrestrial environments. A blue whale grows gigantic not because it hunts giant prey, but because entire oceans contain dense clouds of tiny organisms continuously replenished by nutrient cycles. The sea allows both gigantic hunters and gigantic grazers to exist simultaneously. In some ways, prehistoric oceans may have been even more productive than modern ones during certain intervals. There is also evidence that oxygen levels during parts of Earth's history may have influenced body size, though the relationship remains complex and varies across species. Higher atmospheric oxygen concentrations likely affected some ancient ecosystems significantly, particularly among arthropods and smaller organisms whose respiratory systems depended more directly on oxygen diffusion. For giant marine vertebrates, oxygen availability probably interacted with metabolism, climate, and ocean chemistry in complicated ways still debated by researchers today. Science rarely offers one clean explanation for phenomena this large. Instead, gigantism likely emerged from overlapping factors operating together across millions of years. Buoyancy, food abundance, climate stability, predator-prey escalation, migration efficiency, reproductive strategy, and environmental chemistry all interacting continuously. The deeper scientists investigate prehistoric ecosystems, the more they realize that gigantism was not caused by one magical condition. It was the result of entire planetary systems aligning in ways that repeatedly favored large bodies. Ocean temperature may have played a particularly important role. Warm, ancient seas expanded habitable marine regions across the globe, allowing predators and prey to spread through enormous connected environments. Migration routes likely stretched thousands of miles without the same thermal barriers modern oceans impose today. Large animals benefit enormously from long-distance mobility because bigger bodies often travel more efficiently over vast ranges. Some prehistoric marine reptiles may have crossed ancient oceans the way whales migrate now between feeding and breeding grounds. fossil discoveries from different continents suggest certain lineages spread widely through interconnected marine systems that no longer exist in the same form today. Earth itself functioned differently during many of these eras. Continents sat in unfamiliar positions. Polar ice was reduced or absent during warmer periods. Sea levels rose and fell dramatically. The oceans humans know now are only one temporary version of Earth's marine history. Another factor rarely appreciated is how darkness influences marine evolution. Deep water removes many limitations associated with surface ecosystems. Gigantic animals can move through three-dimensional environments where vertical space becomes part of survival strategy. Large deep-diving predators exploit vast hunting zones inaccessible to smaller competitors. Even modern sperm whales descend thousands of feet into darkness, pursuing giant squid, because the ocean allows movement across immense vertical distances impossible on land. Prehistoric oceans likely amplified this effect. Some ancient marine reptiles possessed eyes suggesting low-light hunting abilities, hinting that giant predators were not confined to surface waters alone. The sea provided not just horizontal territory, but enormous vertical ecosystems layered from sunlight to abyssal darkness. And perhaps that immense spatial freedom encouraged larger bodies to evolve repeatedly, because there was simply more room for life to expand into gigantic forms. Still, gigantism always carries a hidden danger. Large animals reproduce slowly. They mature later. They require more food. Ecosystems supporting them must remain stable across long periods. When sudden disruptions occur, climate shifts, mass extinctions, ocean acidification, changing currents, giant species often struggle first. The same oceans that create giants also erase them repeatedly. Earth's history almost resembles a cycle of biological escalation followed by collapse. Life grows larger, ecosystems become more specialized, then environmental change resets the system again. The sea rewards size until size becomes difficult to sustain. That pattern continues even today. Modern whales face pressures from climate change, warming oceans, collapsing fisheries, pollution, and shifting migration routes. The largest animals on Earth still depend on fragile ocean systems remaining productive enough to support them. In that sense, modern marine giants are not separate from prehistoric history at all. They are the latest chapter in an ancient pattern stretching back hundreds of millions of years. And perhaps the most unsettling realization is that the ocean itself seems almost biased toward creating giants whenever conditions permit it. Again and again, across deep time, unrelated creatures evolved toward immense scale beneath the waves, as though the sea keeps rediscovering the same evolutionary idea. Giant predators, giant filter feeders, giant migrators crossing endless water under open skies. The details change, the species vanish, but the pattern remains. Somewhere inside the physics and ecology of the ocean lies a persistent force pulling life toward enormity whenever Earth allows it to happen. If a human being somehow appeared in one of Earth's prehistoric oceans without modern technology, survival would probably become impossible almost immediately. but not always for the reasons people first imagine. The greatest danger would not necessarily be a giant predator attacking within seconds, like a scene from a movie. In many cases, the ocean itself would become the real enemy long before any monster arrived. Human beings are extraordinarily specialized for life on land. Nearly every advantage our species possesses, endurance running, tool use, fire, complex communication, long-distance planning, depends on stable ground, breathable air, and visibility under sunlight. Remove those conditions. Place a human body into an ancient ocean filled with unfamiliar currents, different chemistry, strange ecosystems, and predators evolved over millions of years specifically for marine survival, and the imbalance becomes almost overwhelming. Prehistoric seas were not simply modern oceans with larger animals added into them. In many eras, they represented environments operating according to ecological rules humans would barely recognize. The water itself often looked different. During warm greenhouse periods, like the Jurassic and Cretaceous, sea levels rose dramatically higher than today, flooding continents beneath shallow inland seas, stretching across regions now occupied by deserts and mountains. Some coastlines extended for thousands of miles through warm tropical environments where marine reptiles hunted above coral systems and dense schools of fish. Other regions descended into darker, open oceans where visibility faded quickly beneath the surface. Depending on the time period, oxygen levels, salinity, water temperature, and even microbial life could differ significantly from modern conditions. A person dropped into those waters would not merely confront ancient predators. They would enter ecosystems entirely outside the evolutionary environment humans were built for. One of the first problems would be orientation. Modern humans depend heavily on stable visual horizons to maintain balance and spatial awareness. Open water removes those references almost immediately. Even experienced divers today can become disoriented underwater within minutes if visibility changes or depth perception disappears. In prehistoric oceans, many coastal waters were likely crowded with suspended sediment, plankton blooms, volcanic runoff, or dense marine life, reducing visibility even further. Ancient seas may have appeared green, black, or reddish, depending on mineral content, algae concentrations, and light conditions. Imagine floating in warm, prehistoric water while visibility drops to only a few feet below the surface. Beneath you lies hundreds or thousands of feet of darkness, containing animals your brain has no evolutionary experience interpreting. Human fear of deep water already exists partly because we cannot see what approaches from below. Prehistoric oceans amplified that uncertainty to an almost unimaginable degree. Then there is movement. Humans are weak swimmers compared to most marine animals. Even elite Olympic swimmers would appear painfully slow against prehistoric predators built for aquatic acceleration. Ichthyosaurs, mosasaurs, pliosaurs, and giant sharks evolved streamlined bodies optimized through millions of years of natural selection. Humans, by contrast, evolved primarily for walking and persistence hunting on land. Our limbs are inefficient underwater. We fatigue quickly. Salt water dehydrates the body. Waves destroy orientation. Even in calm conditions, a human stranded far offshore faces overwhelming physiological stress. In ancient oceans, currents may have been even more dangerous because continental arrangements altered global circulation patterns dramatically. Some prehistoric seas experienced intense storm systems driven by warmer climates and larger, shallow water regions absorbing solar heat. Without navigation tools, shelter, or flotation equipment, a person would likely drift helplessly through ecosystems where almost every large animal possessed enormous environmental advantages. Yet perhaps the most terrifying part is that humans would not even recognize many dangers before it was too late. Modern people instinctively fear sharks because shark behavior is broadly familiar through media and cultural memory. But prehistoric oceans contained predators operating according to body plans humans never evolved beside. Some giant marine reptiles may have hunted from below, like crocodilians, using sudden vertical attacks from darkness. Others likely relied on ambush near coastlines or murky shallows. Certain species possessed enormous eyes adapted for low-light hunting, suggesting they could track movement beneath dim water where humans would struggle to see anything at all. And unlike terrestrial predators, marine hunters do not always announce themselves through sound or visible movement. Water conceals approach. A large predator moving below the surface can remain invisible until impact. Even modern great white sharks sometimes strike seals without the prey detecting danger beforehand. Scale that behavior upward into prehistoric ecosystems filled with larger, more powerful hunters, and human vulnerability becomes almost absolute. There is also the problem of biological unfamiliarity. Prehistoric marine food chains often contained dense concentrations of predators competing within relatively crowded ecosystems. A modern swimmer encountering a shark is statistically unlikely to be attacked. Large marine predators today are relatively spread out across vast ocean regions. But certain prehistoric seas may have supported far greater predator density because ecosystems were extraordinarily productive. Warm, shallow inland oceans filled with fish, ammonites, squid-like cephalopods, marine reptiles, and early sharks created layered food chains where hunting pressure existed constantly. In some environments, large predators may have occupied overlapping territories with little separation. A human body splashing at the surface could attract attention rapidly, not because humans resembled familiar prey specifically, but because struggling movement triggers predatory investigation across many marine species. Another overlooked factor is sound. Humans experience underwater sound very differently than marine animals do. In water, sound travels faster and farther than in air. Marine predators evolved sensory systems capable of detecting vibration, pressure changes, and movement patterns humans barely perceive. Sharks can sense electrical fields produced by muscle contractions. Certain marine reptiles may have possessed advanced hearing adaptations useful in underwater hunting environments. A panicked human swimming inefficiently through prehistoric water would create enormous sensory disturbance compared to native marine animals moving naturally through their environment. In essence, a human in ancient seas would behave like an injured, confused surface animal, broadcasting weakness into ecosystems specialized for detecting exactly that kind of vulnerability. Some prehistoric oceans also contained environmental threats beyond predators themselves. Harmful algal blooms may have occurred periodically in nutrient-rich shallow seas, reducing oxygen levels or releasing toxins. Volcanic activity near ocean basins could alter local chemistry dramatically. Certain marine microorganisms dangerous to humans may have thrived under warmer prehistoric conditions. The deeper one examines ancient marine ecosystems, the clearer it becomes that human survival would not fail because of one cinematic monster encounter alone. It would fail because humans lack the biological adaptations necessary to function inside those ecosystems at all. And perhaps that realization changes how prehistoric oceans should be imagined. The true horror of ancient seas may not have been that giant predators existed. It may have been that humans would occupy no meaningful place within those environments beyond temporary prey or drifting intruders. Even modern oceans remain difficult for humans to dominate without technology. Remove boats, diving gear, sonar, engines, and navigation systems, and people become surprisingly fragile at sea almost immediately. Prehistoric oceans magnified that imbalance beyond comprehension. One especially haunting possibility involves nightfall. Many prehistoric marine predators likely hunted actively in low light conditions. Some marine reptiles possessed enormous eyes, suggesting adaptation to dim water environments. Ancient oceans under moonlight may have become extraordinarily dangerous because visibility at the surface dropped while predators beneath retained sensory advantages. Imagine floating in warm black water beneath unfamiliar stars while distant splashes echo across the sea, and something large moves below where you cannot see it. Humans rely heavily on anticipation and planning to reduce fear. The ocean removes both. You do not know direction. You do not know depth. You do not know what exists underneath you. Prehistoric marine ecosystems turned that uncertainty into a permanent condition. Yet, strangely, humans might still feel awe alongside terror. Many prehistoric oceans were biologically spectacular beyond anything modern ecosystems contain today. Giant ammonites drifted through open water like living, spiraled submarines. Schools of fish stretched for miles. Marine reptiles surfaced briefly beneath orange prehistoric sunsets before vanishing again into deeper water. Coral systems and shallow lagoons may have glowed with immense biodiversity beneath warm tropical climates. Earth's ancient seas were not merely violent. They were alive on a scale difficult to visualize now. And perhaps that is why prehistoric oceans continue fascinating people so deeply. They represent a version of Earth where humans were completely irrelevant. No cities, no ships, no control over the environment. Just endless water filled with creatures evolved through hundreds of millions of years of competition and adaptation. The ocean belonged entirely to itself. In many ways, modern humans rarely experience true helplessness anymore because technology buffers us from most environments. Prehistoric oceans remove that illusion instantly. A person drifting alone through those ancient waters would confront something humanity spends most of its history trying to escape. The realization that nature does not organize itself around human survival. For most of Earth's existence, the seas were not designed for us at all. And if humans had somehow appeared in those oceans during the reign of giant marine predators, the experience would not feel like exploring a lost world. It would feel like entering a planet where our species never belonged in the first place. When most people look at the modern ocean, it already feels immense enough to inspire fear. Cargo ships vanish into storms. Great white sharks patrol cold coastlines. Sperm whales descend into darkness deeper than most submarines ever travel. Entire mountain ranges lie hidden beneath the sea, and vast trenches remain less explored than the surface of the moon. Yet when Earth's full marine history is placed beside the present day, a strange possibility begins to emerge. The oceans humans know now may actually be quieter, smaller, and biologically restrained compared to what once existed. Not empty, not harmless, but reduced from ecosystems that previously supported predators larger, stranger, and perhaps more dominant than anything still alive today. In many ways, the modern sea may represent only the surviving echo of worlds far more extreme than the one humans inherited. For hundreds of millions of years, prehistoric oceans repeatedly produced giant marine reptiles, armored fish, colossal sharks, and ecosystems where apex predators evolved into forms almost difficult to believe were real. Some hunted using jaws larger than cars. Others evolved eyes adapted for black water hunting thousands of feet beneath the surface. Entire inland seas once stretched across continents, now dry and populated by cities, filled with creatures that disappeared so completely that humans only rediscovered them through fragments buried inside stone. The deeper paleontology investigates Earth's marine past, the more unstable the idea of a normal ocean becomes. There may never have been one stable version of the sea at all. Instead, the oceans appear to move through long cycles of escalation, collapse, recovery, and reinvention. Giant predators emerge. Ecosystems intensify. Extinctions erase entire dynasties. Then, new forms rise again from what survives. Seen from that perspective, modern oceans are not the permanent final state of marine evolution. They are simply the current chapter in a much older planetary process. One reason the modern ocean can feel smaller than the past is because many of the largest prehistoric marine ecosystems no longer physically exist. During warm greenhouse periods, such as the Jurassic and Cretaceous, sea levels rose dramatically higher than today. Huge portions of continents disappeared beneath shallow tropical seas rich with marine life. North America alone was once divided by the Western Interior Seaway, an enormous inland ocean stretching from the Arctic to the Gulf of Mexico. Regions now occupied by farmland and deserts once lay underwater beneath ecosystems filled with mosasaurs, giant fish, sharks, ammonites, and marine reptiles. Similar shallow epicontinental seas existed elsewhere around the globe, creating warm, nutrient-rich habitats ideal for supporting enormous food webs. Modern oceans remain vast, but many prehistoric marine environments offer different combinations of temperature, geography, and biological productivity that may have favored gigantism more strongly than today's systems do. Climate also shaped ancient oceans in ways modern humans rarely experience directly. Much of prehistoric Earth was warmer than the present. Polar ice was reduced or absent during certain intervals. Ocean circulation patterns operated differently because continents occupied unfamiliar positions. These conditions altered nutrient flow, migration routes, oxygen distribution, and ecological connectivity across the planet. In some eras, giant predators could potentially travel enormous distances through warm, interconnected seas without encountering the same thermal barriers modern oceans impose. The ancient sea was not only biologically different, it was physically organized differently on a planetary scale. And because ecosystems respond to climate and geography continuously, the marine life evolving within those oceans followed paths modern environments may no longer support. Yet, despite losing many prehistoric giants, modern oceans still carry traces of that ancient tendency toward enormity. Blue whales remain the largest animals known to have ever lived. Sperm whales still descend into abyssal darkness, hunting giant squid. Whale sharks grow longer than many buses while feeding peacefully on plankton. Orcas function as globally distributed apex predators, intelligent enough to coordinate hunting strategies across generations. In a strange way, the modern ocean still remembers its prehistoric history. The giants never vanished completely. They simply changed form. Mammals replaced marine reptiles. Filter feeders surpassed many ancient predators in total body mass. Evolution continued experimenting with scale, but under new environmental conditions shaped by extinction and climate shifts. That continuity matters because it reveals something profound about the ocean itself. The sea repeatedly favors large life whenever ecosystems remain stable enough to support it. Even after catastrophic extinctions, gigantism returns again and again beneath the waves. Still, there are reasons many scientists believe prehistoric oceans may genuinely have supported a level of ecological intensity difficult to find today. One factor is biodiversity structure. Ancient seas often contained overlapping groups of giant predators competing simultaneously. During the late Cretaceous, for example, giant mosasaurs, sharks, large fish, and other marine hunters shared ecosystems crowded with prey species. Earlier Jurassic oceans contained pliosaurs, ichthyosaurs, and numerous marine reptiles occupying layered ecological niches. Some prehistoric seas may have experienced predator densities and evolutionary arms races more extreme than most modern marine systems. Today's oceans certainly contain dangerous predators, but many ancient marine ecosystems appear almost overloaded with large, competing carnivores existing together within warm, productive environments. Human activity has also changed modern oceans profoundly in an extraordinarily short amount of time. Industrial fishing, pollution, climate change, noise pollution from shipping, habitat destruction, and declining whale populations are reshaping marine ecosystems globally. Many large marine animals today survive in reduced numbers compared to historical baselines. Some researchers argue humans have unintentionally created quieter oceans, not only compared to prehistoric times, but even compared to a few thousand years ago. Before industrial whaling, enormous whale populations migrated across oceans in numbers difficult to visualize now. Massive schools of fish once darkened coastal waters. Sharks existed in far greater abundance across many ecosystems. The modern ocean humans experience may already be biologically diminished relative to its recent past, let alone its deep prehistoric history. In that sense, the sea may feel smaller, partly because humans encountered it after centuries of ecological reduction. Yet there is another possibility hidden beneath all this discussion of giant predators and lost ecosystems. Perhaps modern oceans only seem calmer because humans now dominate the planet technologically. Satellites track storms. Sonar maps coastlines. Ships cross oceans daily. Scientific institutions monitor marine species globally. We experience the sea through systems of control and information that prehistoric life never possessed. But remove that technological layer for a moment, and the ocean still reveals how little direct control humans truly maintain over it. Ships still disappear. Tsunamis still erase coastlines. Deep trenches remain barely explored. Entire ecosystems continue functioning in darkness, far beyond ordinary observation. Even now, most people entering open water instinctively feel vulnerable because the ocean never fully stopped being dangerous. It simply became familiar enough for humans to forget how alien it really is beneath the surface. There is also a philosophical tension inside paleontology that makes prehistoric oceans especially haunting. Fossils preserve only fragments. Entire species vanished without leaving complete skeletons. Soft-bodied organisms almost disappeared from the record entirely. Ocean floors recycle through tectonic processes over millions of years, destroying enormous amounts of evidence permanently. What humans know about ancient seas is therefore incomplete by definition. Every reconstructed ecosystem is built partly from absence as much as discovery. That uncertainty leaves open the possibility that some prehistoric oceans were even more biologically extraordinary than current evidence suggests. Perhaps larger predators existed whose remains were never fossilized. Perhaps entire ecological interactions vanished without trace. The ancient sea will always retain some level of mystery because too much of it disappeared before humans evolved to observe it. And maybe that is why prehistoric oceans continue exerting such a powerful pull on human imagination. They represent both memory and absence at the same time. A lost Earth beneath our own. A reminder that the planet existed for unimaginable stretches of time before human beings arrived, filled with creatures moving through ecosystems we can only partially reconstruct from scattered bones and buried sediments. The ocean today still feels vast to us because human lives are short and our perspective is narrow. But against the scale of Earth's full marine history, modern oceans may indeed be quieter than what came before. Not dead, not empty, but softened after repeated cycles of extinction and recovery. The terrifying giants that once ruled prehistoric seas are gone, yet traces of their world still remain hidden beneath the surface. In the movements of whales, in the darkness of deep trenches, in fossil teeth buried along forgotten coastlines. In the instinctive fear humans feel when staring into open water too deep to see the bottom. Because somewhere beneath that fear is an ancient truth the planet has repeated for hundreds of millions of years. Long before humanity ever crossed the oceans, the seas already belonged to creatures far larger and far older than us. And for most of Earth's history, the ocean was never truly ours at all. Thanks for exploring the ancient oceans with me tonight. If you enjoyed this journey through the lost world of giant sea monsters, don't forget to subscribe to Sleepy Earth channel for more relaxing prehistoric documentaries. And before you drift off, leave a comment sharing what part of the world you're watching from tonight. Sleep well, and good luck surviving the ancient seas.